Alexander Graham Bell was asked, how people might use the telephone. You know what his response was? They're going to listen to opera from home. He never even thought of the idea that people would want to talk to each other by telephone. When you ask people who are involved in inventing something, their opinion on how it might actually get used, they are invariably wrong.
Welcome to the At Scale podcast. This is actually our 4th episode of the podcast. Today we're having a conversation with Dr. Sindhu right before his keynote in today's Networking at Scale event. Dr. Sindhu started his career at Xerox PARC, went on to work for Sun Microsystem, and eventually founded Juniper Networks. Then recently went to Microsoft after the acquisition of his other startup, Fungible. Our goal with At Scale is to tell the real stories from the leaders like Pradeep to the technologies and systems that are shaping our world. Today, we will cover a lot of topics, ranging from Xerox PARC, the inception of the World Wide Web, the rise of Juniper, up to the latest challenge created by the advancement in AI, including special chip design. What was the tone in terms of what was the leadership of that place asking from you, and what did they do special to make it different?
So, I arrived at PARC in 1984, and it was just after Bob Taylor and Butler Lamson and Chuck Thacker had left to go to digital. So the mood at that time was not fantastic because the cream of the crop had left. But what PARC did was to provide an environment for people to explore in the area of computer systems. And that environment was still there. And the first project that I worked on was actually called Dragon. It was, if you would believe it, a project to build a multi-processor workstation. And at that time, machines were about, I think individual CPUs were around 1 MIPS.
Yep.
And the goal was to give to every researcher a 100 MIPS machine. And the only way you could do it was to put together a bunch of CPUs, and that was called Dragon. So my first job was actually to design elements of Dragon. And I did that for probably 2.5 years, maybe 3 years, coming up with the first cache coherent algorithms for multiprocessors. And that work eventually led to Xerox collaborating with Sun.
With Sun, yeah.
To build the SPARC Station 2000, actually SPARC Center 2000, and SPARC Server 1000. Those are the 2 machines that came out of that work. But the environment was, people were free to think, and it was encouraged that people had to think and actually produce good ideas. But it was not a pressure-laden place.
Yeah.
And we also had very, very interesting visitors come from universities from abroad, a lot of flow from Carnegie Mellon, MIT. So that made it a very, very interesting environment for somebody who was just coming out of grad school.
So you came out, and how did you know about this place? Like was it something known in grad school, or?
Absolutely. So Xerox PARC at that time. So this goes back a ways. In 1976, when I just joined Carnegie Mellon to get my PhD, we received the first batch of Alto computers.
I see.
It was a new world.
Okay.
The first time you see a bitmap display.
Yeah.
First time you see a machine where what you see is what you get.
Yeah.
In terms of printing.
Yeah.
And that's also where I met Andy Bechtolsheim.
Okay.
Who was a fellow student at the time. And so everybody knew about Xerox PARC. And there was a lot of flow back and forth in faculty and people from PARC visiting CMU as well. So it was well known.
That's amazing. Yeah, like for me, my exposition to I got exposed to Xerox PARC. I was younger. I was probably a teen, early teen, back, I come from Canada. So back in Canada, like at that time, probably like you can imagine like IBM PC Junior era type of thing. And I remember waiting in line somewhere at not a convenience store, but like a regular store. And I wanted to buy, at that time, it was a word processor that was coming from like Ventura, I believe it was the name. And this is how I got exposed to that world, because like, I'm like, oh, this is the first time you can edit with a UI. And I remember finding a way to order a mouse from the US, like it was $400. And I was 12 years old. And I got exposed to that world. It was like quite the fantasy. Like, it was like...
the contrast, I remember the first time I saw an Alto. Prior to that, we had an Apple II, I think.
Yeah, Apple II, Apple II.
Was sitting in the same lab, and people would play with it and so on. It was a green screen and the whole works. And along comes the Alto with a completely different experience. And it's literally, the responsiveness was fantastic. Even today, machines have a hard time keeping up with that, interactivity.
That interactivity. Nice. I'm just going to do a little bit of recap for the audience. Like, we're now in the middle of networking at scale. We're recording this during the event. You will have a talk later. I hope that...
Looking forward to
it. Yeah. I hope this session will help, and you'll be ready for the talk. Today, there's a lot of the buzz is all around AI. See it in my job every day. You see it too. You have a very interesting talk today, and which I can almost summarize like, hey, a lot of it will be about discipline and going back to basic. So what do you believe right now is important, like in this new era of AI, where we see the demand for computing and capacity and networking growing at the speed that is tremendous?
Absolutely. So one of the things that you see is AI is an enormously potentially disruptive force, disruptive to the way of doing things, and the amount of compute required, and consequently the amount of network required, because this is a scalable problem, has been growing at about 4x every year. And it shows absolutely no signs of slowing down. But, the same thing that happened during the internet, where people's expectations initially were completely outlandish.
Yeah.
And when those expectations weren't met, things quietened down for a bit. I expect the same thing to happen here, but at least the basis of my talk is, hey guys, if we keep ourselves grounded on fundamentals, then you're likely not to make too many mistakes. You might still make mistakes, but they won't be egregious mistakes. So that's it's to try to ground the audience on the fundamentals of networking.
Great. Do you feel like talking from the beginning of the internet, do you feel like this time right now we're kind of at the inflection? Things are starting to pick up. There's a lot of ideas. There's a lot of stuff that I'm looking at and I'm like, oh, this makes no sense. I will never use that. Do you feel like we're back at the beginning of the World Wide Web, where things are growing? And do you see some difference?
I think it is true that when you ask people who are involved in inventing something, their opinion on how it might actually get used, they are invariably wrong.
Wrong, yeah.
Because I think I don't know whether this is apocryphal or not. Alexander Graham Bell was asked, how people might use the telephone.
Uh-huh.
You know what his response was? They're going to listen to opera from home. He never even thought of the idea that people would want to talk to each other by telephone. So I'm probably the wrong person to ask, but what I do know is that, and I believe this for a very long time, that human beings will never have enough compute power at their disposal, because compute power is arbitrarily useful. And AI just happens to be the latest application, phenomenally interesting application, that the amount of compute that is needed is just essentially unbounded, I would say.
Yeah. And do you feel like things are like from a technological standpoint right now, the progress that we're making, do you feel it's going in the right direction? Or like, I also have the same feeling that, hey, it will need to take a break to have like meaningful use case so that we can kind of like narrow down, oh, this is working and this is what we need.
I think the use cases are still, the really interesting use cases are still to be invented. Clearly, programming is one of them.
Yeah.
And it is one of the most successful ones. I think also that there is some possibility that scientific discovery would be speeded up dramatically. The only caveat to that is, and this a lot of people miss, almost all the models that have been trained, they've been trained on an abstraction of the real world.
Yeah.
The language is an abstraction.
Yeah.
It's not the real world.
Yeah.
And we should not forget that.
Mm.
So this is why these models are exceptional at anything which is linguistic or can be represented as a kind of language, programming language, or anything else that resembles that. When it comes to actual discovery or modifications of physical law, these AIs would need to actually interact with the real world in some way. So that is yet to be determined.
In terms of like, that's for the use cases. In terms of like hardware evolution, if I contrast a little bit with the rise of the web, if my memory is correct, back then in the early days, we used to have a lot of specialized hardware. Yeah, like Spark 20 to run these like web workload, and then you used to have like all sorts of different like appliance. And then after everything stabilized and we started to apply constraint because there was not that much money in the system, I will call it like the Google approach started to standardize. Like we put like pizza box, very simple, and then we kind of focus on the software itself. I'm feeling that I'm seeing the same thing with AI right now, where like, okay, we have a lot of these custom chip, custom CPU, special network. Do you feel like we're done with that like hub?
No.
Or like?
So you make a very interesting point. It seems like early in any technology, people try a lot of different variations.
Yeah.
I mean, going back to whether you look at networks or you look at processor design, there's a lot of variance. And very quickly, things get standardized on one, maybe two architectures. And the reason for that is that you want some standardization so that you can get this cumulative effect of lots of users using it.
Yeah.
And then people developing it, and the volume becomes high of a given type of machine. Now, it's especially true when hardware is involved, because it doesn't make sense to build 100 chips, 100 units of a new architecture. This makes no economic sense. So I think things will settle down with specific types of computing engines. Very likely the engines for inference and the engines for training will be different because there's different ratios of compute power to memory bandwidth to networking in both of these.
Yeah.
I mean, the other thing that I would watch out for is that to me, it's clear that transformers are not the be-all and end-all of the world. People will discover other architectures that perhaps work even better, maybe for different problems, if not for language processing. And so there's a tension here about, should I be designing my engines to be more general?
Yeah.
Or should I really focus on the transformer architecture? And different startups are taking different approaches to this problem.
How does that brings me to another question. Like, looking back at your bio a little bit, you worked at a startup before being in Microsoft, and you work on the data processing unit.
Mm-hmm.
Can you explain to me, like, what was the goal of that, and how is it different from like general purpose CPU versus GPU? And
so you had mentioned earlier that in the early days of the web and after, there was a lot of focus on software for general purpose CPUs.
Yes.
Now, general purpose CPUs are a fantastic invention. And they are just that, general purpose. You can, that almost anything is Turing complete with relative to anything else. So you can write any algorithm on them. Once the scale-out architecture started by Google and Facebook and Amazon and Microsoft, once this architecture took hold, let's call it a scale-out architecture, if you look at the actual workload that machines are exposed to, a good percentage of that, I'd say maybe 30% of the workload, is what I would call data-centric.
Mm-hmm.
And I define a data-centric workload as one where I/O dominates compute, not the other way around.
Yeah.
The moment you have that, general purpose CPUs don't perform very well. In fact, they perform terribly. And it's, again, going back to fundamentals, CPUs are designed to get very high performance on single-threaded applications. And when you try to do that, you actually pessimize the design for a heavily multi-threaded workload, which is the kind of workload that is data-centric. Examples of that are network stack, storage stack, security stack. And so that was the insight back, I think, in 2014, when I was still at Juniper. And I thought it was important to try to address that problem. I tried to do that from inside Juniper, but that the company didn't want to go in that direction. So I decided to step outside to develop what then became the DPU to focus on this very problem. And what we were able to demonstrate is some 20 to 30x performance per watt improvement. So those are not small numbers.
Yeah, 20x, no.
It's very hard at any point in technology to get those kinds of numbers. And these numbers approach the numbers that Juniper improved compared to...
On a packet forwarding initially.
Packet forwarding of IP packets on general purpose CPUs compared to specific
like
silicon
A6
design.
Yeah.
Yes.
Okay.
Exactly.
And then what is the pattern in the DPU? Like, is it something that you're more optimized? For example, when you're on I/O, you have your thread that's waiting for I/O, and then you wait. Like, and when the data becomes available, you load it on the register and so on.
There are two aspects of it. One, which is that all the work that arrives at this machine comes in the form of packets.
Okay.
Either packets on a network or packets on PCIe. Doesn't matter. They're both
the same. Okay.
On PCIe, they're called TLPs. On the network, they're called packets. But if you look at the packets arriving on either of those networks, actually, I shouldn't call PCIe a network, either of those interfaces.
Yeah.
What you see is that the packets are multiplexed over many, many, many different streams.
Yeah.
Thousands of concurrent streams. Well, if you now expose CPUs, general purpose CPUs to this workload, you are going to multiplex these CPUs to death. And multiplexing is bad for CPUs because everything that you do to get high performance single-threaded computations requires you to have state very close to the CPU, and multiplexing just destroys that completely. So the design had to be rethought. And in fact, the main problem that we did solve is how do you get high performance for this specific workload, but at the same time, make the engine be programmable in a high-level language like C or C++. Now, some people don't call C a high-level language, but relative to writing microcode, it surely is a high-level language.
Okay, that makes sense. I'm looking forward to use that one day in data warehouse type of application.
That design is actually very, very good for layer 4 through layer 7 computations, like in load balancers.
Load balancing, security rules.
Exactly. It's exceptional at those things, but also for databases And now we're looking at applications like vector search, which I think it will also excel at.
Great. Going back a little bit in time, you were at Xerox PARC, then you did create with some people, you did Juniper. Okay, I remember watching an interview of you and saying like, oh, you're not that good at managing people. Do you remember like some of these challenges at the beginning of Juniper when kind of like, hey, the world is changing right now, so you have a super fast-paced technology, and then you have to lead a bunch of people in the same direction. So do you remember some of these challenges?
I have never been great at managing large teams of people, but I've been very fortunate that from my school days to be surrounded by really exceptional people. So I love working with small teams of great people. And at Juniper, I was very lucky to actually put together such a team and focus on the problem. And so actually, within the first 6 months, I was a CEO for the first 6 months. Yeah. People may not remember. I asked my board for help to find a CEO. I said, look, it looks like this opportunity is fantastic and that I don't want to screw it up with my ego. So I'm going to step aside as CEO. Let's find a CEO. And we indeed found the first CEO. His name is Scott Krenz, as you probably know. And he led the company for the next, I'd say, 8 years.
Yeah.
So that's how that turned out.
That's great. For the record, I also appreciate small team, not too big, very highly efficient.
Exactly.
Low bandwidth communication.
This is exactly the issue. And one thing I'll tell you that was striking as Juniper grew, the problem we were trying to solve, the technology problem, was a problem of scaling the network. And some of the issues that you see in scaling teams is exactly the communication problem.
Yes.
It's kind of eerie that the same problem shows up in both places. The problem of scale.
Yes. And contrary to network, sometimes your layer 2, layer 3 switches are adding noise.
Exactly.
Versus the network, at least they only forward packets.
And that's right.
Yeah.
Yeah, they don't inject noise into the system.
Exactly. And now with what you learn at Juniper in this big tech transition, or let's call it up-leveling of tech, what would you suggest that people having a startup today, or focusing on what AI can do, what pattern should they apply? What strategy should they apply?
Unfortunately, there's no secret formula for a successful startup. For example, my fungible adventure, I would call it. It's not I would say, a successful startup. It's successful in the sense it was not economically successful. We did produce a technology that is very successful and is being used at Microsoft. But it's not the kind of economic success that most people join startups.
Yeah.
What I would advise people, if I'm to give any kind of advice to people, is number one, focus on fundamentals.
Yeah.
Because especially during periods of hype, if you get carried away by the noise, you will make mistakes. That's number one. And number two, you need to have taste in picking a problem. And this is very hard to do. So the problem needs to be difficult enough that not every Tom, Dick, and Harry can solve it in their garage. And it needs to be interesting to lots and lots of people. So that combination is rare. And it was present at the time that Juniper was born, for sure.
And do you feel that it takes time to get to you need experience. You need to be have lived that problem over and over to kind of be able to bubble it up and say, okay.
I think that some experience in, I will only say things about systems in which I have some expertise. In systems, you have to have actually built things. Just writing papers about it is not sufficient. So experience is necessary. But the other attribute that is phenomenally important is to keep your ears and eyes open. And today we have tools in AI that I would have dreamt of having early on.
Yes.
And so each individual can be personally way more productive than ever possible. And so that's the really exciting part about what's to come.
Yeah. The power of summarization that AI has, the power for me is almost like if you take something like, I don't know if you've used Notebook LM from Google, where you can attach a bunch of papers and reference, and then you read the paper and you're like, okay, I have a ton of questions, and start having the conversation with the tool and kind of like getting an answer and going deeper and deeper is just like tremendous.
I haven't used Notebook LM, but I have done exactly as you say in trying to understand one or two papers which are in a particular area and to go deeper and deeper and deeper. And you get a level of understanding much, much deeper than you would have had you just read the paper and made notes.
Yeah.
Because you can ask precise questions about where your doubt is,
yes,
or where you are missing a key concept, etc.
I was even surprised that I was able to ask the model, give me some examples of this. And I was like, I was blown away.
Yeah. I mean, just yesterday, for example, I had a particular algorithm that I wanted to evaluate. So I asked the question and I gave it some specific examples. And I said, hey, tell me what's an upper bound and a lower bound for the number of compares for this particular problem. Well, within 5 minutes, I had the answer. So these things are, anytime you have a technology that saves people time, it is worth its weight in gold, honestly. And certainly AI does that.
So we cover a little bit the idea of a startup. And then people have a good idea, they start something, and eventually, there's difficult times. So from what you have learned over the years, example, at Juniper, at your second startup and so on, what people need to be ready for, like the difficult time? What sort of mindset do they need to have? Because it won't be rosy every day.
So, my Juniper experience actually spoiled me because things were pretty rosy most of the time. But you still have hiccups and gotchas, no matter which company you talk about. And you have to have the faith. First of all, it's not faith as in just belief, but you have to have, based on logic and on your understanding of what's possible, given the available technology, you have to have the belief that you can actually carry this through. And it's at difficult times when that belief gets shaken the worst. And what you need to do is that project that to the team. Another thing that's really important, I think, in a startup, and actually the reason why startups succeed or fail, is whether the leader can keep the alignment.
Yeah.
Think of people almost as magnetic domains. If the domains are pointing in different directions, there's no net magnetic field that comes out. But if they are aligned, then you have a very strong magnet. That's a similar thing in a startup, that if everybody's aligned with the direction that the company should go in, well, then the speed is much, much faster.
And then you get to a better outcome.
Exactly. Now, I would, again, separate technological success from economic success. And that, that's a matter of timing.
Yeah.
For example, if you're too early or too late, if your timing is wrong, no fantastic team, no amount of money will actually solve the problem. The timing is very important too.
Yeah. Now, if I go back to the at-scale community at large, in this AI transition, now we go, okay, you have a great idea, and then you will find an obstacle, and here's the mindset. Where do you see opportunity for various AI breakthrough or, idea of startups or?
It's a complex question because there are, probably half a dozen different layers at which you can innovate, starting with the models. And we already talked about, hey, is Transformer the end of the story?
Yeah.
I think likely not. And there's clearly innovation going on in algorithms for LLMs. And, the most interesting work is happening at the big companies simply because the stuff requires a lot of resources. So I'm not sure that a startup is a great place, unless you have a team which is well known and so on and so forth.
Yeah.
You could attract a ton of money and then actually do good work. Then there's a layer below that, which is the stratum of software that sits between the model and the engine that you're building. I actually don't know of any companies that are working on that specific layer.
And you're talking about the layer for training, or like post model when you get like more
either one of those. I'm talking about lower level. Like, for example, it's the stuff that you write directly on CUDA.
Okay. Yeah.
Okay. It's a layer that might make the GPU that you use agnostic.
Yeah.
You could replace one with the other.
We absolutely need this.
We need it pretty badly. Correct. Then there is the design of the engine itself that does the work. There is plenty of innovation to do in the networking. Because this problem, by the way, if it could be solved with a single GPU, then we wouldn't be talking about networks.
Yeah.
But it's a heavily parallelizable problem. And so networking is integral to solving the problem. The other area which is in networking, which is very important, is the interconnect, the physical interconnect, the logical layer. And I'm going to talk about all these layers in the keynote later today. Packaging is phenomenally important. One of the things that's happening now is, given the compute density requirements imposed by GPUs, packaging is one of the hottest areas of advancement. You're approaching packaging densities which are unheard of just 2 or 3 years ago. And along with packaging densities, you're also getting I/O densities. This is the number of bits per second per cubic inch, if you want, is also going through the roof because the network requirements get dragged along with the compute requirements. I think the issue with innovating in those areas, packaging, is that, again, it's very, very capital intensive. And it's companies like TSMC or Broadcom or other companies that can afford to make these investments. So nonetheless, I think in the physical interconnect area, there are startups which are trying to solve this problem of how do I build an interconnect, a medium which has the characteristics of copper in terms of cost and power and reliability, but has distances of around 10, maybe 15 meters instead of just 2 meters.
Yeah.
So that's a very, very important problem. And there are several startups working on that problem because it's isolated. And if you nail it, you solved a very big problem.
Yeah. And it gets intersected with also like even like the more physical stuff, like how do you cool this thing?
100%.
The building.
Yep. So there's that. It's a very, very complex problem. And when you're building, say, a facility which is close to a gigawatt, there are lots of physics problems, topology problems, math problems, bin packing problems.
Yeah, bin packing.
It goes on and on. It's very complicated. It's very multi-dimensional and multidisciplinary, I would say.
Yes. We can feel it. We can feel it like that. Everything is moving, data center design, the way we interconnect, the units that we use to represent what I call a region now are suddenly like becoming monster region that we never had before.
Exactly. And it's putting pressure on virtually every aspect of technology. Power generation, power delivery, cooling. It just goes on and on and on.
With all that said, are you hopeful that this technology will make us better?
I don't want to project into the future, but I'm always optimistic. I'm optimistic that this technology can actually help human beings do a lot more things that are interesting. Unfortunately, technology has always been a double-edged sword.
Yeah, it is.
That no matter what technology you think of, for example, the ability to fix nitrogen.
Yeah.
Something that was invented by Fritz Haber in Germany. You could make fertilizers using that technology, saved a lot of lives. On the other hand, you can make TNT, explosives. A lot of people were killed that way. This technology is no different.
Yeah. No, I'm very well aware. All right. Well, thank you so much for your time.
You're welcome, Francois.
That was great.
Yeah.
And we'll let you get ready for your talk at Networking at Scale.
Well, thank you for all the excellent questions. Enjoyed it very much.
Same here.